Hi viewers, welcome to all. Here we are discussing about a project power efficient tiny Yolo CNN using reduced hardware resources based on both multiplier and Wallace adders. The convolutional neural network, often known as CNN, has achieved a high level of accuracy and being used extensively in an image identification process. Recent years has been a proliferation of current applications that are powered by deep learning, which presents a formidable obstacles for the research and development of hardware implementations. As a result, the hardware optimizations for the effective accelerator design of CNN continues to the difficult problems. A processing element that is responsible for carrying out the convolutions operations is an essential part of the architectures and the accelerators. Okay, this article presents a novel processing elements designs as an alternative method for the implementations of hardware. The goal of this design is to lower the quality of the hardware resources and the amount of power reduced. It has been suggested and proposed that the modified both multiplier with the encoding technique and velocity based adders may respectively take the place of a bulky MAC unit and the usual adder trees. The multiplier architectures will occupy number of conventional full adders. It will take more logic sizes compared to the Exarmux full adders design. Here we have presents this work with the Exarmux full adder design instead of conventional full adder design. Finally, this work was developed in Verla HDLs and synthesized in Xilinx Vertex 5 FPGA and compared all the parameters in terms of area, delay and power. Okay, now we can verify the base paper. So here what they are doing means they are doing a multiplication part at 16 bit size. Okay, but in the existing multipliers we have both multipliers separately and velocity multipliers separately. Okay, so both multipliers here we are focused for to reduce the number of partial product, and velocity multipliers will focus for to reduce the number of partial products addition. Okay, so based upon this the combinations of this both encodings versus velocity multiplier part will be proposed here. Okay, with a mat unit for CNN applications. Okay, so here they have given some CNN escalators in figure 5, the parallel architecture of the proposed CNN escalator design unit. It's a processing element. So this is a processing element. Okay, this part we have planned to implement with the multiplications and addition part. Okay, so this part will be described in the multiplications. Okay, so here the figure 7 shows the velocity multipliers WM for CNN escalators. Okay, so here once you are given an input and weightage, okay, it will come with the MAC unit, replacing MAC unit. Okay, so inside of this is hand operations and velocity reductions will be applicable. Okay, for it's a normal multiplication, but we have proposed with this architectures using this method, the figure 8. Okay, the MBE modified both encoding multiplier. Okay, so here we are given as a multiplier is an input and multiplicand is an input to the both encoding logic. The both encoding will create a both algorithms with the encoding and decoding part. Okay, after that it will be given the partial product generator, the partial product output given to the accumulation part. Okay, and accumulation output given to the CPA. Okay, carry propagate adder. Okay, and this both encoding we have used this reference paper. Okay, so design and implementations of the advanced modified both encoding multiplier. Okay, so you can refer this paper. So this is a technique and architecture of the encoder of both simple encoder and decoder. Okay, and this paper also will have designed the same technique. So how this both multiplier versus velocity multipliers will be work here. Okay, the multiplicand and multiplier given to the both encoder. Okay, and the output of the both algorithms given to the velocity additions, and the output will be taken from the CLA. Okay, but we are used CPA, and our proposed is the Exarmux full adder. Okay, so here, so this is a architecture which is A will shows the MBE multiplier with the sign extensions. Okay, and B will show the MBE multiplier with sign extensions eliminations. Okay, and C will show the MBE multipliers along the velocity addition. That is a proposed work about this paper. Okay, and so this work we have developed in Yolo HTML code. Okay, so here, so this is a 16-bit for convolutional method. So this is a test bench and this is a top model. So here in the top model we have connected the multiplier and multiplicand. So the multiplier it given to the booth encoding. So the booth encoding output given to the partial product generator. Okay, and the partial product generator output given to the Wallace tree. Okay, after that it will given to the CPA. The booth encoding logic, this is a booth encoding logic, so it will have number of booth algorithms. Okay, so booth algorithms contains a booth encoders and booth decoder. Okay, so booth encoder and booth decoder code also. Okay, so here this part simulations it will be shown here. Okay, clock it is at multiplier, multiplicand, product output. So this is a multiplication check, error difference error. Okay, so this is a top model. Okay, you can check this 3 output. Okay, so this one. Okay, and this same part we have developed in Exarmux full adder. Okay, so this is Exarmux full adder architecture. So using this Exarmux full adders we have designed the optimized compressor also. Okay, so as per this architecture. Okay, so figure 10 it will be shown the exhaust compressor, first compressor, and optimized implementations of first compressor. These 2 models we have designed for comparisons. Okay, so this coding also we have completed, and this is a simulation for the optimized thing, and so this is synthesis report for conventional method. Okay, so this is a conventional method. Okay, here you can check the number of LUTs, occupied slices, IO base. Okay, and you can check the RTL schematic. Okay, so initially we will given the multiplicand and multiplier data to the booth encoding logic. So this booth encoding logic, okay, so this booth encoding logic will have number of booth algorithms. Okay, so here this is a booth algorithm. So each booth algorithm will have a booth encoder and booth decoder. Okay, okay, so after this booth encoding we are given the data to partial product generator. So this partial product generator will receive the data and place the data as per the 0 1 2 3 2 power 0 1 2 3 logic. Here 0A 2A minus A. Okay, as per that. So we have created a partial product A0 B0 A0 B1 A0 B2 A0 B3 A0 B4 up to A15 B15. We have to generate the partial product. Okay, that all partial products given into the Wallace tree additions. Okay, so here this is that Wallace tree. Okay, and this Wallace tree will have number of compressors. Okay, exact compressors. Okay, so these are the exact compressors, number of full adders. Okay, so here this is a 16x16 multiplication, right? As per that the architectures will be designed here. Okay, okay, so once the Wallace tree part completed, we are given all the data to CPA, carry propagate data, and finally we are taken as a final output. Okay, so that output is the simulations. Okay, you can use a calculator and you can calculate this 49 into 28 and 53 into 34. Okay, and 61 into 46. Okay, whatever results you are needed, you can check it. Okay, and the same for we have synthesized in Exarmux based architectures. Okay, this is a logic size, LUT, slice registers, IO based on okay everything, and this is a RTL schematic for Exarmux. Okay, and this comparisons results we are updated in the comparisons document. Okay, so here you can check the comparisons, number of slice LUTs, occupied slices, bounded IO base, delay and power. Okay, the variations for existing and proposed. Okay, and we have written abstract document of this project. Okay, so here this is the title, base paper abstract, and improvement of this project, proposed title and proposed abstract. Okay, existing systems disadvantages and proposed systems advantages. Okay, and related notes. Literature survey, finally references. Okay, thank you.
If you need more video related to VLSI project, please like and subscribe this channel.